Welcome everybody. It's Chem 112 during the Summer 1 session during COVID time. It's going to be an interesting semester. What I'm going to attempt to do is bring you a lecture experience similar to what you would be experiencing when you were in class. So Mark Schraff is my name. I will not be in the Chemistry Learning Center because you won't either, but this is a place that you can always hit me up whenever, but make sure you hit this address, not my Mix account, because I do not receive my Mix emails for some reason. So I will be contacting you using Mix through eCampus. But don't respond to those. Instead, always respond to mschraff@wvu.edu. That's the ones that I get. Basically, I am available to you whenever you need help. So all you need to do is contact me and I'll be glad to help. Emails, pictures of your work, these are all good things whenever we're talking to each other, as opposed to I just don't get chemistry. Tough to answer that via email. So specifics are better, and we'll try to get information out to you on a daily basis, maybe even multiple times each day, to get you up to speed and keep you up to speed. So communication is key. We'll find a way to do that. Your textbook is the GOB Structures of Life 6th edition by Timberlake, and your lab text is the survey book in 112. Your lab professor is Dr. Trina Perrone, and she will be contacting you soon with specific information about the labs. Okay, so on we go. All right, so let's talk about homework this week. Reading the syllabus and making sure you have the textbook and lab manual are important. eCampus is basically where you will be getting your grades, and I will be using it to send you emails. So that's going to be the main place to go, but you need to go there. Clearly, we're not going to need an eye clicker, and you won't have a lab room. You won't need to wear lab goggles. We will not be having this, and basically when you're doing your lab work, you can dress any way you want. Start working on homework problems is always going to be helpful. Those won't be posted. You'll know what they are. You're also just occasionally going to perhaps be visited auditorily by my cat and my dogs, or my dog and my cats. So we'll have to deal with that as we go. That's Abby, by the way, and the clickety-clack of the dog walking away, that's Daisy. So let's keep going. Okay, studying. Well, let's see. How's the best way to study for chemistry? Abby really wants you to do well in this class, so you got to work hard. Active participation. If you just listen, just watch, just passively hope that watching these videos are going to make the difference for you, it's not going to work. You've got to do the homework and complete it, and do it on time, not the night before, but continuously. Remember, we are taking an 18-week class, and we're squeezing it into 6 weeks. So it is a tough row to hoe. You're going to be on this every day and every night. That means read ahead and do not fall behind. Do works every day. I'm not going to be in the learning center, so you can't work with that. Forming study groups online with other people in the class is a great way to do things. But if you're not working on this every day, if you wait until the night before, you are not going to get done. You are not going to be successful. So get on it, stay on it, work hard, and ask questions to me via email. Remember, the address is mschraff@wvu.edu. That's the best way to get your questions answered. Okay, so what's our next step? Well, our next step is reviewing the stuff that you're supposed to already know from Chem 111 so that we can apply it to Chem 112. And some of the stuff you haven't done in a while. So it's very good that we get on it, stay on it, work on it, and make sure that we're good at it, because these are the basics that you're going to need to understand organic chemistry reactions. So anytime you're talking about bonding, you have to determine the right kind of bonding. We will learn that in organic chemistry, covalent bonding is the most important, but we have to deal with ionic bonding as well. So there's two different kinds of bonding that can occur. Transfer of electrons from a metal to a non-metal to form fully charged species. That's considered ionic bonding. And when two nonmetals share electrons, notice that whenever the two are sharing the electrons, that this first atom feels like it owns 1, 2, 3, 4, 5, 6, 7, 8 electrons. And this atom also feels like it owns all 8 electrons, including both of those shared electrons. That's what a covalent bond is all about. So octets means 8, and that's the stable place that atoms like to have 8 electrons, full electrons in their outer shell or empty outer shells. This helps to be more stable, and that's the driving force for every reaction, is to get to a more stable state. Atoms will do this by losing, gaining, or sharing their outer shell or valence electrons. Two different ways, as we just discussed. Ionic bonds formed between metals and nonmetals, or between two polyatomic ions. And if you look on your syllabus, there's a big long list of all the different polyatomic ions that can help you. Not a bad idea to memorize those. And that's as compared to covalent bonds between, mostly we'll deal with 2 or more nonmetals in which they're sharing those electrons. Okay. So we talked a little bit about the reasons, the driving force for chemical bonds occurring. After all, if you had a baseball and you tossed it against a wall, or even let it sit up against the wall, or even rubbed it against the wall, there wouldn't be a chemical reaction there. Why not? Well, it's because there's no way for that to happen such that a new substance would form, because there's no extra stability that would occur if they did try to react. And if they don't do that, they're not going to react. One of your jobs in this class is to be able to look and determine what kind of reaction is going to occur. So, just as a review, octet is 8. Octets don't occur with H or HE because they're small and they're in the first row of the periodic table. And whenever that's true, they only are going to be satisfied with 2 valence electrons. Okay, so keeping the octet rule in mind, let's look about a little bit about how reactions tend to occur and keeping that 8 electrons in the outer shell process in place. Okay, so how do we go about deciding? That's a really important thing. If we see compounds, we'd like to know what kind of bonding would occur, because that controls an awful lot about the activity and the physical characteristics and also the chemical characteristics of that compound. The kind of bonding is an important part of trying to understand the molecule itself. Well, a simple rule that can be helpful here is metal plus metal makes no compound. Instead, it makes just a mixture. Brass is a mixture of melted copper and melted zinc. And the reason why you know it's a mixture is if you melted just the zinc and the copper and poured them together into a mold and then let it freeze, you'd have a trumpet. But then if you took that trumpet and you heated it up so that just the copper or just the zinc would melt and poured that away and then melted the other one, you'd get right back to where you started. So a mixture is not a chemical compound because you can go backwards and make what you made before or what you started with. Can't do that if you crack an egg, right? So metal plus metal makes no compound. Metal plus non-metal makes, ionic bonding. And a non-metal plus a non-metal makes covalent bonding. Okay, so if you have a periodic table out and handy, and that's always good anytime you're working through any kind of chemistry lesson or chemistry lab or lecture or problem, you always should have a periodic table out. If you identify where magnesium is, it's on the left-hand side. We'll see this in just a second, but if you look at the periodic table and you look for that special stair steps, and it's easy to tell whenever you look at a good, useful periodic table, metals are on this side, and it's easy to tell because you'll have zinc and copper and silver and gold and all the things that you know are metals are on the left. On the right of the stair steps, these are the nonmetals, things like sulfur and oxygen and chlorine and argon, and anything that's along the line are considered to be metalloids. They're sort of both. They have metallic properties as well as non-metal properties. So magnesium is all the way over here in group 2A, and chlorine is all the way over here in group 7A. We'll do this a little bit more in just a second, but clearly that's metal plus non-metal, and so you would expect that to be ionic bonding, right? Here we have hydrogens and carbons, so these are all non-metals. So you would expect this one to have covalent bonding. Here this is a non plus a non. Right, go through and see what you think the answers would be. Sure, covalent. Potassium is in group 1A. Bromine is just below chlorine in group 7A. So this is metal plus non-metal. And that's going to be ionic bonding. And then we've got non-metals here. Then we've got bromine. So this is going to be something that's sort of interesting. We'll have to talk about this because you might expect this to be ionic. But remember, this all is non-metal, and this is considered a non-metal as well. So we've got covalent bonding instead. Let's see if we're right. Ionic here, covalent, covalent, ionic, and covalent. Okay, so let's review that a little bit more with the periodic table. Okay, so this is a huge deal to be able to look at the periodic table and recognize just by looking what you would expect the kind of compounds to get formed. Here's the stair steps that we talked about. Notice that the lines are a little bit darker here than the other. So that's the line of separating the metals on this side from the non-metals on the other side. Now, you should pay careful attention to these. These are the group names, and there's a big difference between the B's and the A's. The B's are transition metals. Everything in this sort of dip down middle part and then out to the end here. These are all the transition metals, and they can make variable charges. They can make different kinds of charges, and you can't tell just by looking at a copper or at a cobalt or at a nickel whether the charges are going to be +1, +2, +3. Chromium can make +1, +2, +3, +4, +5, or +6, and you can't tell just by looking. But for the group A elements, you can tell. So that means the first 2 columns and the last 6 columns. And you can tell because what the A group numbers tell you is the number of electrons in the outer shell of every atom in that column. And that's the sort of the cool part about the periodic table, is that everything is arranged in the columns such that helium, neon, argon, krypton, xenon, and radon, all except for helium, which has 2, all of them have 8 electrons in their outer shell. Okay? So the way we think about this is we say everybody in group 1A has 1 electron in their outer shell. And every atom in group A wants 0 or 8. And they'll do that the easiest way possible. So if you have 1 electron in the outer shell and you want to get either to 0 completely empty outer shell or 8 completely full, it's much easier to lose that 1 electron. And when you lose an electron, you lose a -1. So you end up making a +1 ion. And everybody, hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, they all like making +1 ions. Everybody in group 2A has 2 electrons in their outer shell. They'd rather get to 0 than to 8, so they're going to make +2 cations. Group 3. 3 electrons, easier to lose 3 than to gain 5 to get to 8, so they make +3 cations. Carbon can either lose 4 electrons to get to a +4 or gain 4 electrons to get to a -4. But we'll find out that carbon likes to do different kinds of bonding than ionic bonding. Remember, this is all for ion formation. Nitrogen, because it has 5 electrons in its outer shell and wants to get to 8, will be more likely to gain 3, so it makes a -3 ion. And you can see how that works for oxygen. 6 electrons gains 2 to get to 8. Fluorine, chlorine, bromine, iodine, 7 electrons like to gain 1 to get to 8. And neon, argon, krypton, everybody in group 8A, including helium, has already full outer shell, doesn't want to react, and that's why these are called the inert or noble gases, because they don't like to react. They don't need to. They're already completely stable and satisfied. So this is something that was a review for you from 111. Just running by it again. If you have questions about it, please go back to your beginning chapters or ask me questions. So this is not necessarily about ionic bonding, but predicting how many bonds an element will like to make. And the idea is if you have a single electron out here, then another electron likes to come in to get shared from an outside source. That's a bond. Whereas if you have what's known as a lone pair or a non-bonding electron pair around that atom, that part's already satisfied, and so it's going to want to make 3 bonds to have 3 extra electrons come in so that it can get to its full 8 electrons around its outer shell, its full octet. That's why everybody in group 1A likes to form 1 bond because it has 1 electron. Because BE is in group 2A, it's going to form 2 electrons and has no lone pairs. And then we jump down. Obviously, in the pattern stays the same. If we look at oxygen, oxygen has 2 lone pairs and 2 single bonds, and so we'll like to make 2 bonds. All right, no bonds here because no space to get extra electrons. Okay, so that means the position on the periodic table can also help you predict how many bonds an element is likely to make. Pretty useful. So we look at nitrogen. Nitrogen is in group 5A. So if we are going to take those 5 electrons, we go 1, 2, 3, 4, and then we'd stick an extra 1. I don't know why I did that line. Sorry about that. So that means 1 lone pair, and would like to make 3 bonds. So C is your answer there. So that means looking at the Lewis dot structure, you remember those from for elements, can help you remember and understand how many bonds a particular element is going to be likely to make. And boy, that becomes really important when we talk about organic chemistry and organic molecule formation. Okay. Lewis structures. So we have to have a consistent method, systematic method for drawing Lewis dot structures. And the first thing you have to do is count all the valence electrons, all of them. Remember that whenever you're making an anion with a negative charge, you add 1 electron to make that compound more negative by 1. And cations, since they're plus charges, you're going to subtract the electron because electrons are being taken away. So you get the total number of electrons, you divide by 2 to get the electron pairs, because you have to use up all those electron pairs around all the atoms so that everybody's satisfied. Arrange the atoms next to each other. That's called the skeleton structure. You know, the leg bone connect to the thigh bone connect to the shin bone, all that stuff. So it's how the atoms connect to each other. You had a whole bunch of bones from a skeleton that was all scattered. You wouldn't stick a foot on top of a shoulder. And foot goes where it goes, and the carbon in a methane molecule goes in its spot, and the hydrogens go in their spots. We will be helping you with this because that's one of the things that you're going to learn is basically how the atoms want to connect to each other. Okay, so first thing, whenever we go to fill in the electrons around the atom to get the Lewis dot structure, you want to connect the atoms first with single bonds, which are what 2 electrons are. Then you take care of the surrounding atoms, the outer atoms. Hydrogen only gets 2. And then if there are extra electron pairs, will go on the center atom. And you use multiple bonds if octets aren't completed. And again, you just need to do some practice to get good at this. It'll become important. Multiple bonds, double bonds, triple bonds, we're going to use that a lot in our class, so you'll have to be on top of that. Let's do some practice. Okay, CH5N. Well, one thing you know can't happen is you can't go CHHHHN because, let's look right here, that hydrogen has 2 electrons from that bond and 2 electrons from that bond, and that's not going to work, right? That's too many electrons. So hydrogens can only ever be outer atoms on any kind of compound. So how will we go about doing this? Well, we have to count up all of our electrons, right? So carbon, 1 times 4, because carbon is in group 4A. Hydrogen, 5 times 1. And nitrogen, 1 times 5. This is the valence electrons. This is the number. And when we add those up, we get 14 electrons. We have to divide by 2, which means 7 pairs. Okay, so how do we do 7 pairs? Well, how do we connect these guys? Well, I'm going to help you out a little bit with that. Okay, so that's the skeleton structure. We've connected the 2 inner atoms, and I'm counting out and showing you the order that these go in just so that you can tell. I guess we don't have to do that since you're doing a video. Now let's connect all the outer atoms. That's 2, 3, 4, 5, 6. Well, we have only 6 pairs used. We have to use all 7. Carbon can't take any more, but that nitrogen needs 1 more electron pair. Okay, and before you go, you should check and make sure everybody's happy. The hydrogen feels like it owns 2 and it's happy. And that's true for every hydrogen in the compound. The carbon feels like it owns 1, 2, 3, 4, 5, 6, 7, 8. Because remember, this line equals a single bond with 2 electrons. So that's 8 electrons for that carbon, and it's happy. And now let's look at the nitrogen. 3 bonding pairs, 1 non-bonding pair makes 8 electrons. That's a happy camper. So what do we got? This is the Lewis dot structure for that compound. Good. Let's try another one. C2H5Cl, chloroethane. Okay, quickly, we look at carbon. 2 times 4, 8 electrons from there. Hydrogen, 5 times 1 again. 5 total valence electrons there. Chlorine has 7 electrons in its outer shell. So when we add that up, we get 20 electrons. Divided by 2 is 10 pairs. So we have to distribute 10 pairs around these 5, 6, 7, 8 atoms so that everybody's happy. The carbons will attach to each other. We'll stick hydrogens around the outside. And then we have a chlorine attached here. Okay. Single bonds between the carbons and the hydrogens. Single bond between the carbon and the chlorine. That's a total of 1, 2, 3, 4, 5, 6, 7. We have 3 more electron pairs that we have to add. This chlorine only has 2. So let's stick lone pairs on the chlorine. Notice that the chlorine has 2, 4, 6, 8. Happy. Carbon, 2, 4, 6, 8. Happy. I don't want those to look like anything more than single bonds. Carbon, 2, 4, 6, 8. So everybody's happy with single bonds everywhere, and that's the Lewis dot structure for that compound. All right, let's try again. Okay, we're given that framework, that skeleton structure for the compound over here. We have to count up our lone pair, or our electron pairs, to decide how many we need. Carbon, 3 times 4, or 12. Hydrogen, 6 times 1. In every hydrogen has 1 valence electron, so that's 6. So that's 18 divided by 2 is, by 2 is 9 pairs. Okay, so how do we do 9 pairs here? Well, let's connect. 1, 2, 3, 4, 5, 6, 7, 8. All right, now we have another electron pair that we need to stick somewhere. Now where might we put that? Well, we can't put it on the hydrogens, right? They're where they need to be. We have 1 electron pair. Notice that if we stuck it here, this carbon wouldn't be happy. And if we stuck it here and not there, that carbon wouldn't be happy. So what we actually have to do is make a double bond. I better erase. There we go. So this carbon feels like it owns 2, 4, 6, 8. This carbon feels like it owns 2, 4, 6, 8. And this carbon feels like it owns 2, 4, 6, 8. So everybody's happy. We've made a double bond here. Now let's talk a little bit about polarity. We've used exactly 9 polarity. Pairs. I sort of think of bond. So that makes this the stable Lewis dot structure. Somebody's often stronger than somebody else, and therefore they're going to be able to pool closer. And when we talk about pool, we're talking about the electrons, and it's within a bond to start with. Okay, so the periodic trend for electronegativity is really pretty easy. Fluorine wants to steal everybody's lunch money. It's the strongest kid on the playground. So fluorine is up here in the upper right-hand corner of the periodic table. So En goes down as you move left, and En goes down as you move down. All right, so just think about fluorine as being the baddest. Wants the electrons more than everybody else, and then everybody just wants them less. So once we make that decision and that idea of understanding the periodic trends, you can start to decide in general, especially if you get the electronegativity values, which we would supply you with those. You don't have to memorize those. You can get an idea of what the polarity of each bond is. When it's a nonpolar covalent bond, that would be the case if chlorine and chlorine were bonding. They have the same exact electronegativity value, so one chlorine isn't stronger than the other. So that's completely equal sharing of the bonding electron pairs. And basically, if you're within 0.4 of somebody else that you're bonding with, it's going to be essentially even bonding. Now, you can also have polar covalent bonding, so we're still sharing the electrons, but we have unequal sharing. Somebody eats more of the ice cream cone than the other person, that kind of thing. So if the electronegativity difference between the bonding atoms is a bit bigger, between 0.5 to 1.9, then we consider those to be polar covalent bonds, in which the chlorine is really good at grabbing the electrons compared to the hydrogen. And so the hydrogen is going to be partial positive, and the other atom in the molecule, in this case, the chlorine, is going to be partially negative. It's not full charges like an ionic bond. Those are with En values of 2.0 and up. That's how you know you'll have an ionic bonding partner or an ionic bonding compound, is if the En differences are 2.0 or greater. Okay? Oh, okay. They showed what I showed. Alrighty, we have the basics of Chem 111 and the material that you brought into the class where you already pretty much know what's going on. So now it's time to really get digging into organic chemistry and what's going on. That's our introduction. We'll give you some of the, and we're going to do this for every kind of compound that we deal with this in the class. Characteristic features, shapes, how to draw them, looking at particular functional groups, and then talking about their properties. We're going to be doing this for all the different kinds of compounds that we deal with. So let's get started. When we talk about organic chemistry, we're talking primarily about carbon-based compounds. There's a famous old Star Trek episode where a monster that lives in the rocks, is misunderstood. They think it's terrible because it's killing all the colonists on this planet, and it turns out that it's just a silicon-based life form, not carbon, but silicon. And that's interesting because silicon is right below carbon on the periodic table, which means it wants to make 4 bonds just the way carbon does. So there are theories out there that say that there's no reason why there couldn't be a silicon-based life form out there with conditions being right. But on this Earth, our conditions are such that basically all life is related to carbon-based compounds. And for all these products that you see here, clothes, food, medicine, gas, refrigerants, soaps, all of those things have a relationship to organic materials and organic compounds and live things anyway. So this is a very important topic. There are natural sources of organic, and then there's synthetic, meaning reacted. So we're going to be diving into this pretty deep, but we'll get the basics in first. So methane, natural gas, and it's completely odorless, which means if you smell natural gas, you're not really smelling natural gas, you're smelling a little bit of a stinky compound that's included within the methane so that you can detect whether or not there's a leak. Ethanol, some of you may be familiar with. That is the particular alcohol that is in booze. These are typical and very small organic molecules. There are also some much bigger ionic or covalent compounds, capsaicin. It's right there on the label. It's basically something that irritates your skin and brings analgesic relief in the form of lymph and nerve responses to try to alleviate that response, that heat feeling. I am drinking right now. There it was, my coffee, and it's a very popular and relatively safe stimulant, I should say, and looks like a very complicated molecule, doesn't it? As does this. Well, all of biology is almost entirely made up of very large molecules in which chemistry happens in very small spots. And that's the essence of what we're going to learn in this class. Figuring out the very small spots that the chemical reactions occur in large biological molecules. All right. A couple more examples. Different fruits with different aromas and therefore different tastes. And scientists have isolated the actual molecules that contribute to these aromas. Benzaldehyde for cherries and almonds, Citric acid is the tartness for fruits. Ethyl butanoate is that wonderful pineapple smell. And isoamyl acetate gives you the odor of banana. Now, there's obviously lots and lots and lots and lots of other compounds that are in each of these biological materials. But this is what chemists do. You want something to taste like cherries? You might want to see if you can isolate benzaldehyde and then stick it in your candy or your artificially flavored cherry thing, because that's what you're going to smell and therefore taste. It's sort of interesting. All right, so some all organic compounds, all of them contain carbon atoms. Hydrogen atoms are in almost all of them as well. That's why we talk about hydrocarbons a lot, because carbon and hydrogen both in the compound. Now, we remembered from the Lewis dot structure of the atoms that carbon likes to make 4 bonds and hydrogen likes to make 1. So they're sort of a perfect match for each other, right? If that's the hydrogen in each one of these, and that's the carbon with its 4 dots, you can see where the hydrogen is going to want to come along and give its dot up in a shared responsibility, so that we 2 electrons single bond and we've made methane. Happy hydrogen, happy hydrogen, happy hydrogen, happy hydrogen with 2 electrons each. And then the carbons are happy with 4 bonding pairs, or a total of 8. So everybody's happy, everybody's satisfied. And that's why methane is a stable molecule. Carbon likes to form single, double, or triple bonds to other carbon atoms in order to make everybody happy. Remember, the electrons in a bond are shared between both bonding partners. So this carbon right here feels like it owns both of those bonding electrons, and this carbon here also feels like it owns both of those. Think about it. If you have a roommate in your apartment, you pay half the rent and your roommate pays half the rent, but you both feel like the entire apartment is yours. Let's pretend that there's no bedrooms. It's just a square room. Well, you would feel, whenever you brought people over, you'd say, here's my apartment, and you'd say it's the whole thing, and your roommate would do the same, even though each of you is only contributing half the rent. So that's how covalent bonds go. And clearly, if it's carbon with carbon, that's going to be a non-polar covalent bond, because they're going to have the same electronegativity value. So 2 electrons shared is a single bond. That's 4 electrons shared for a double bond, and 6 electrons shared for a triple bond. Some more characteristic features of organic compounds. There's lots of organic compounds that have chains of atoms, and others develop ring structures. So a chain just sort of keeps going, like your ankle bone connected to your shin bone, connected to your knee bone, connected to your thigh bone, connected to your hip bone. And then there's other kinds in which rings are formed, where they connect to each other and obviously make a ring structure. And different characteristics, both chemical properties and physical properties, can occur with compounds that make chains, either linear or branched, or in ring structures. And this is all stuff we're going to study. Characteristic number 4 for organic compounds. There can be other elements other than carbon and hydrogen. And whenever there's some other atom that's involved in the organic compound, that other atom is called a heteroatom. And we've already talked and recognized for heteroatoms those characteristic number of bonds that they're likely to make, depending on its location on the periodic table and the Lewis dot structure of the atom. And so everybody on the compound always has to still have an octet, but depending on whether you have a nitrogen, which likes to make 3 bonds, oxygen, which likes to make 2, sulfur is in the same group as oxygen, so it likes to make 2, fluorine, chlorine, bromine, and iodine are all in the same group, so they like to make 1 bond. And oxygen is the most common multiple bond. We'll see that a lot as we start to go through the functional groups. Once again, another reiteration of what we just talked about is the idea that hydrogen is going to make 1 bond and has no lone pairs. Carbon likes to make 4 bonds. Remember, that could be a double bond and a triple bond, 2 double bonds, a triple bond and a single bond, that kind of thing. But carbons rarely have lone pairs. They like to just go ahead and make bonds. Nitrogen often has that lone pair. Oxygen has 2. And the halogens, the group 7A elements, all of them make the same kind of compounds because they all have 7 electrons in their outer shell. And they're going to have those 3 non-bonding electron pairs or lone pairs, and will like to make 1 bond. Okay, and that becomes helpful whenever we go to try to describe the structure and the electron environment in our organic molecules. Oh, okay. The number of bonds plus the number of lone pairs has to equal 4 for everything. Let's go back. That's the tetrahedral drawing. Each of these bonds angles are the same. This is coming out at you, so this is like an atom and an atom. These little dashes means it's going away from you. And this is in the plane of CA. Up here at the top is in the plane of the paper. So the A's go with the dashes go into the like into your computer, and the A with the wedge is coming out at you. So there's like 3-dimensional. Three bonds, 1 lone pair means that, remember, a lone pair you can't see. It's still there. And it's still repulsive To me, I think of it as a lone pair is sort of like I don't know, breaking wind on a elevator. That's the nicest way I can say it. You can't see it, but boy, you know it's there and it's repulsive, and so you're going to get away from it. So you can't ignore if it's a lone pair, but whenever you go to see the shape, you can't see it. So I hope that if you put your thumb over the top one, let's pretend that isn't there at all. Can you see that that looks like a triangular pyramid? Can you see, if you then can't see another one, if you have two lone pairs, that that is a bent shape? Okay. Three groups is a trigonal plane, so that's all in the same plane. I think of plane as in a propeller, like a plane propeller, and it's two-dimensional, so it's flat. 120 degrees between every atom and the center atom. And then if it's two groups, that's clearly just a line. And if one of these was a lone pair, like say this one, it's still there, but you can't see it. That's still bent just like this one, only maybe a different angle. This was stuff that you dealt with before, and whenever we go into your first couple of labs, you're going to be dealing with shapes of molecules a lot. So the visualization of the shapes of molecules is of primary importance in understanding organic chemistry. So it will be important to you to brush up on this if it was one of those subjects that you weren't especially good at in Chem 111. So, examples. Let's see. I want to make sure that there isn't something else that gets added here. Okay, so 1, 2, 3, 4 means 4 places with electrons. 4 places where you find electrons. No lone pairs. No lone pairs on the center atom. Because 4 places means tetrahedral arrangement. Every time. Gets arranged in a tetrahedral configuration. No lone pairs means shape is equal to the arrangement. So it's a tetrahedral shape. Now, there are 4 places here as well. Okay, 1, 2, 3, and then the lone pair. So, tetrahedral arrangement. But 1 lone pair on the center atom therefore the shape is trigonal pyramid. It's going to look like a tripod. Okay. That's how we need you to be thinking about shapes of molecules. Few more. 1, 2, 3, 4 places again. So this is a tetrahedral arrangement. I know it looks linear, doesn't it? It looks like it's just straight across, but you know better. You know that a tetrahedral arrangement means oxygen's in the middle. We got a lone pair up here and a lone pair here, and an H and a CH3. And since you can't see these lone pairs, the shape is bent. You look here, there's 1, 2, 3 places where you can find electrons. A double bond is just a stronger magnet. So this is trigonal planar arrangement and shape, because there are no lone pairs. And clearly, for this carbon, 1, 2 places, that's just a real strong magnet. So there's 2 places. Anytime it's 2 places, it's just plain old linear. Okay, so this is the way you need to think about it. Remember, Lewis dot structure does not tell you shape. Lewis dot structure tells you the arrangement, the geometry. The number of places with electrons. That's all it tells you. It doesn't tell you what the shape is going to be. That's your job. You need to be able to figure that out. Okay. Next thing we have to worry about with organic molecules is how to write the formulas. Some organic molecules are enormous. And if we had to write down every single atom and every single bond, we'd run out of paper, and it would be very, very difficult, especially whenever you think about the fact that, like I said before, with most biological processes, anything that has to do with a biological reaction is a great big molecule dealing with another molecule, and the chemistry that goes on is in a tiny little spot. So the rest of it doesn't do anything. So it's more important to be able to focus in on the place where all the business happens, the important parts. So let's talk a little bit about molecular formulas versus condensed formulas versus structural or expanded formulas. It all depends on the best way to draw these things. Let's just discuss what a molecular formula indicates: the number and type of atoms in the molecule. The number and types of atoms in the molecule. But what it doesn't do is say anything else. It doesn't tell you how they connect. So I'm going to see if what we have here. Okay, so CH4. 1 carbon, 4 hydrogens. C8H18. This is octane. This is methane. And we'll understand how to do our naming soon enough. But notice that it doesn't talk at all about how atoms connect or the type of bonds that are present. C12H22 O11 is sucrose. No idea how things are bonded. But it still is informative because it tells you exactly the atoms that are in the molecule and how many of them there are. Okay, now the condensed formula is a little bit more informative because it places them sequentially to give you the idea of what the bonding order is. So for something like butane, which is C4H10, we would write butane in a condensed form as C3H2 or CH2, CH2, CH3. Notice that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens and 1, 2, 3, 4 carbons. So that's a molecule that has 4 carbons and 10 hydrogens. So we would call that butane. You can also write a condensed formula even more condensed by repeating units as such. So that was what butane looks like in a condensed formula. Okay, now the structural or expanded formula shows each atom and each bond. So let's go with butane again. And what butane likes to do is each atom and each bond. So you can see that we're showing every single connection and type of bond between all the atoms in butane, basically the Lewis dot structure. 4 carbons, 10 hydrogens, single bonds everywhere. That is the structural formula, the expanded formula. And the line formula is much more shorthand. And again, this is all to make things easier for us as we write out formulas of compounds, because if you can make some assumptions, then things get a lot simpler. So it assumes a carbon for a line formula at each intersection when a line changes directions and at the ends. And the hydrogen atoms are left off. So for C4H10, we would go 1, 2, 3, 4. Remember, there's a carbon at each end and at each intersection. And then there's hydrogens on each of these. So you can see where the translation between the structural and the line formula is simple. You can see where it works. But boy, it's so much easier to just write that. 1 carbon, 2 carbons, 3 carbons, 4 carbons. And that's what butane is as well. So you're going to have to be good at all of these in order to be able to properly talk about and transfer to me your knowledge of organic molecules. All right, so a little more discussion of condensed structure organic molecule drawing on your end. There's a lot to this drawing of organic molecules. I am a sloppy mess when it comes to it. Organic professors and organic chemists are beautiful at it. You just need to be better at it, as good at it as you can be, so that I'm not especially picky. I just need to know for sure that what you're writing down is correct. So you can see that CH3 is sort of this chunk. The CH2s are these chunks, if you wanted to look at it that way, but that really is more similar to that guy. So what would the condensed formula be? A CH3 on this end a CH3 on this end and 2 CH2s in the middle. CH2, CH2. Okay? So that's the expanded formula. And there's that condensed formula. CH3, CH2, 2 of them in the middle, and then a CH3 at the end. There are times when it's very helpful to draw more information in to really get across the idea of what kinds of bonding is actually occurring in a molecule. Because again, it's all about the bonding. That's the important thing about the molecule. So we want to see the places where the bonds are forming. So if we were going to try to go from the line or structural formula to the condensed structure here, CH3 corresponds with this part. CH corresponds with the brown part. We can stick this CH3 that's sticking up here. Notice that's still just a CH with that looking at it, that attached on the left here, that attached up top. And then we've got a CH2, CH3 at the end. CH2, CH3 at the end. So a carbon bonded to only one hydrogen looks like CH in the condensed structure. Okay, and you can condense things even further if needed. We already talked about writing this double CH2 together. CH, sorry about that. 2CH3. But you can also look at this as there are 2 CH3 groups attached to that one carbon. So you could write this as CH3, 2CH, which means that that carbon has a hydrogen attached, 2 CH3s attached, and then it's got a CH2 attached to that with the CH3 at the end. All of those mean the same thing. So you have to be able to go from structure to condensed or from condensed to structure. It's important. Practice. Here we go. They don't. Okay. So let's go. So we're going expanded. Structural formula. We're going to show all the atoms and all the lines. So CH3 is H, H, and H. CH2, 3 of them, which means that's a chain of 3 CH2s in a row. Okay, now what comes next? An O. So you're just following along. Oxygen likes to make 2 bonds one to that previous carbon, one to the next carbon with 3 hydrogens. But you can't be done here, right? Because the oxygen right now only has 1, 2, 3, 4 electrons. It likes to make 2 bonds, and it likes to have 2 lone pairs. So that's the structural formula for that compound. All right, let's try the next. CH3 at the end, H, H, H. Now we've got a CH. So we can draw a C and an H. And that means that that is a CH3 that is attached to that carbon. And now we've got 2 more CH2s on the chain, H and H. And then we finish with a CH3 at the end. It's always good to go back, count, and make sure that you have the right number of carbons and hydrogens and oxygens and all the different elements in the compound. So we've got 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. 3, 4, 5, 6, 7, 8, 9, 10, 11, 14 hydrogens. Do we have 14 hydrogens here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Good. All right, so that's the compound. It's not pretty, but it gets the job done. Okay, what's next? I hope you can identify that this carbon has to have 4 bonds to it. This is one of the carbons that's attached in the chain. There's a hydrogen that's attached to the chain. And this is telling you over here that there are 2 CH3CH2 fragments that are attached to that carbon. So carbon, CH, H, 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 but then we do that again, CH2, CH3, so that takes care of these 2 that are attached to that carbon. It has a hydrogen attached, and it's got a CH, H, Br. Okay, so 1, 2, 3, 4, 5, 6 carbons, right? 1, 2, 3, 4, 5, 6 carbons. 3, 4, 5, 10, 11, 12, 13 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Got that right? 1 bromine. Okay. Let's take a look at this last one. There's a CH3 group. Then there's 2 other CH3 groups that are attached to that one carbon that has no hydrogens attached. So that means that there are 3 CH3s that are attached to that carbon right there. So H, H, H. Oh, that's my next cat. That's Wiggy. Hi, Wiggy. Hi. You're very encouraging. Good boy. There's going to be a CH3 up here. H, H, H. And an H, H, H down here. And then we continue on with the chain. That carbon has an H on it. And then it's got a CH3 and another CH3. So basically, you have to follow along and make sure that you're paying attention to what the condensed structure tells you, and you just fill in the fragments of the molecule as it goes. And there's no good way to do this by memorizing. There's only one good way to do this, and that's by practicing. Practice, 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 practice. I cannot insist enough that if you're good at doing all of these examples on your own, and then you're good at doing all the homework problems, that you'll have no problem with the tests. But if you just look and say, oh, it makes all the sense in the world, not going to go well for you. All right, another try at this. Let's make sure that it doesn't just fill in. Okay, so now we're going to go from structural formula, from expanded formula into the condensed, and then we can further simplify it as well. So the key to this is to identify similar groups that are attached to the same carbon. Similar groups that are attached to the same carbon. That's why these carbons are highlighted, because we can condense this, make it simpler. Nothing better than simplifying things by saying we've got a CH here, CH, that has a CH3 on one side and a CH3 also attached. And then what's after that? A CH2 right here. Then you've got something similar. A CH with a CH3 on the end and a CH3 sticking out of the bottom. So I guess we're sort of doing this. That goes with that. Then we've got that and that going with these. Okay, and if you want to further simplify this, since the circles here and the boxes here are the same, you can say that there's two CH3 fragments sticking on a CH, then there's a CH2, then there's another CH with two CH3 fragments sticking off of that. All right? And whenever we do B, this one's, I guess, a little simpler. You're looking at this part and saying that's the repeating unit. And that's what the condensed structure allows you to do, is to take away all the bonds. And then if you want to further simplify it, take into account the repeating units. So CH3, CH2, CH2, O, then CH2Cl is the condensed structure of that original structural formula. And then we can simplify it a little bit. There you go. Okay, so again, it's about simplicity. It's about making things go a little faster whenever you're writing things on exams, that kind of thing. Okay. So I swear I checked this. We did it already. Okay. So how about some rules for skeleton structures being converted into line formulas. Whenever we have rings and chains in which things are repeating and it's the same thing over and over again, the line formula is very, very useful, not only from a simplicity's sake, but also getting an idea of the important parts of a molecule to the less important parts as far as chemistry goes, reactions. So, when we're drawing those skeleton structures, every junction of any two lines, and at the end of every line, you have a carbon. And you always have to make sure that the carbon will have its 4 bonds, because that's what carbon always wants to do. Not 4 single bonds, but 4 total bonds. If you have a heteroatom, because it's not a carbon or a hydrogen that's attached to a carbon, you have to draw those in. And if the heteroatom has a hydrogen attached, that's when the hydrogens have to be drawn in. And you don't have to draw the lone pairs in on heteroatoms, but I sort of like it because that becomes something that's real important when it comes to chemical bonding and reactivity down the road. So it's good to see those. Okay. So let's go for this guy. I think we've seen this before. 1, 2, 3, 4. 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens. So 1, 2, 3, 4. So that's how you sort of run it whenever you're doing this. There's 1, 2, 3, 4. So that's the skeleton structure. That's it. 1, 2, 3, 4, 5, 6, and then there's a carbon on the line, the end of every line. So 1, 2, 3, 4, 5, 6. So how will we go about doing this last one? We'll think about the chain part. 1, 2, 3, oxygen, carbon. So 1, 2, 3, oxygen, carbon. That's good. What next? Remember, there's going to be a carbon sticking off of that second carbon. We can stick our lone pairs in on that oxygen. We can stick a chlorine on the end of this carbon. Remember, that doesn't mean that there's a carbon here at the end of this chlorine. It just means there's a chlorine here attached to that carbon. And as a result, remember, this carbon will have 1, 2, 3 hydrogens. This one will have, that's a carbon there, so that has 1, 2, 3 hydrogens up there. This carbon has a bond to carbon, a bond to carbon, and a bond to carbon, so it would need an H there. This one needs 2 H's, right? That's that hydrogen and that hydrogen. Now we've got the oxygens with their 2 lone pairs. This carbon is bonded to a chlorine and an oxygen, so it would need a hydrogen and a hydrogen. So that's the way you think about this. Now, if you erase all the hydrogens, all you have is line, line, line to the oxygen, line down to that carbon, and then the chlorine with the carbon up here attached at the end of the line. So that looks about the same. That looks about the same. Let's see what this one looks like. I'll look at it pretty good. Same deal. Got it? Okay. This is the part that might be the most confusing, but that is not a carbon. If it has a heteroatom attached at the end, that's the last carbon in the chain. That's a chlorine attached directly to that carbon. Okay. Let's see here. Cyclopentanol is a 5-carbon ring. So 1, 2, 3, 4, 5. 1, 2, 3, that's terrible, 4, 5. But if there's one thing you're going to learn from me is that it doesn't matter what it looks like. It just has to relay the information well. And we've got an OH attached at this carbon right here, which means this carbon right here. That looks about right. Now, one of the important things to be able to do is to recognize on any line structure where the extra hydrogens that have left off have to be. And the key to remember this is that carbon has to have 4 bonds. And so whenever you're leaving off the hydrogens, you have to make sure that they have the proper number of bonds to it. And those bonds are going to be supplied by the hydrogens. So this is a carbon, this is a carbon, and that's a carbon, right? And so is that, and that, and that, and that, and that. I mean, it just goes on and on and on. Every intersection not the ones that have a heteroatom attached, but every intersection has a carbon. Now, how many bonds are on this carbon right now? 1, 2. So that means you need 2 more hydrogens. H, H. So the answer is 2. Now, how many does this carbon need? How many bonds does it have? 1, 2, 3. Right? There's a bond, there's a bond, and there's a bond. So it needs 1 hydrogen. How many does this one need? 1, 2, 3, 4. That one has 0 hydrogens attached because it's already got its 4 bonds. So that's the process by which you have to go about thinking about this. Okay, not too bad. C2, 1, 2, 3 bonds, so that would need 1 hydrogen. Guess we did it for this one up here. C3, 1 bond, 2 bond, 3 bonds, so it needs 1 hydrogen. Female sex hormone estradiol. Fairly complicated molecule, and yet we're going to find it's not very. Okay. So now let's add on our hydrogens to all of these guys to make sure that they have the proper number of bonds, proper number of hydrogens. And you have to remember that carbon is going to make 4 bonds. Nitrogen is going to make 3 bonds. Oxygen is going to make 2 bonds. And that is going to inform how many hydrogens you have to add on. So, starting up here in the upper left-hand corner, it has 2 bonds right now, so I'm going to need 2 hydrogens to make a total of 4. This has 1, 2, 3, so I'm going to need 1 hydrogen. This has 1, so I'm going to need 3 hydrogens. Okay? Pretty simple. This carbon has 3 bonds, so I need a hydrogen to make it 4. This has 1, 2, 3, 4. You can't stick a hydrogen on this carbon because if you did, it would have 5 bonds on it. So that doesn't happen. How many bonds does this carbon have? 1, 2. So that means we're going to stick a hydrogen bond here and here. This carbon has 1, 2, 3. It needs 1 hydrogen bond. This carbon has 2, so it needs 2. Pretty simple if you keep this in mind, and that you get in mind from the Lewis dot structure of the atom itself, which is easily looked at by looking at the number of electrons that are in the outer shell of each of their atoms, which comes from their group A designation. So that periodic table is really helpful, isn't it? Okay, so down here, needs 1 bond, needs no bonds, because 1, 2, 3, 4 for that carbon. This carbon has 1, 2, so you're going to have to stick 3, 4 to get its 4 bonds. Now, oxygen likes to make 2 bonds and have 2 lone pairs, right? This is a typical mistake. They leave off the hydrogen that has to be attached to that heteroatom, and then it has its 2 lone pairs. Cool. All right, next guy over. This carbon only has 1 bond, so we're going to want to stick 3. This carbon has 1, 2, 3, 4 bonds. It's happy. What about this oxygen? Is it going to want to have a hydrogen on it? Nope, because the oxygen has 2 bonds already, so no hydrogen goes on the oxygen, although if you want, you can stick 2 electron pairs on that oxygen. This next carbon has 2, so it needs 2 more bonds. That will be the hydrogens that are missing. This oxygen has 2 bonds, so all it will have are the lone pairs. That carbon needs 3 hydrogens. It's a simple deal if you keep this stuff in mind. Okay, let's do this one fast. Carbon has 1, so it needs 1, 2, 3. Carbon has 1, 2, 3, 4. It's done. Oxygen has 2. It's done. We'll stick lone pairs on that. Nitrogen likes to make 3 bonds. How many does it have right now? 1. So it's going to make 2 more bonds to the hydrogens. And it likes to, because it needs to end up with 4, it'll have the lone pair on the nitrogen. Okay? Finally, let's do the little ring here. That carbon needs 2 more bonds. That carbon needs 2 more bonds. That nitrogen needs 1 bond and 1 lone pair, so that it ends up with its 4. All right, that's it. I promise you, you're going to see that on tests, so be ready for it. All right, so how do we go about doing that? Well, what I like to do is make sure I have the carbons attached everywhere they need to be attached. That's the backbone first. Then add the hydrogens. So, carbon, 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 carbon. This guy needs 1, 2, 3 more hydrogens. This guy needs 1, 2, 3 more hydrogens. 1, 2, 3 bonds for this carbon, so it needs an extra hydrogen. 2 bonds for this carbon, so it needs 2 more hydrogens. And 3 more bonds, so it needs 3 more hydrogens. And that's it. It just doesn't take long. I think it's a lot easier to take a line formula and turn it into a expanded or structural formula than the other way around. But still, it's doable. Let's do the backbone first. Carbon, 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 carbon. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That's the picket fence part. Then we stick a carbon on top here. And then on the next one over, not this one, but this one, next one that's sticking up, there's 2 carbons. 1, 2. Okay, and then once you do that, you just fill in the hydrogens. H, 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 because that needs 4 bonds. H, H, because that needs 4 bonds. H, H, because that needs 4 bonds. You get the theme here. 1, 2, 3 bonds. That needs an H. That needs 2 more H's. 1, 2, 3 bonds, so that needs 1 more H. 1, 2, 3. 1, 2, 3. Then don't forget these 2 bonds on that carbon, so that needs an H here and an H here. And then that needs 1, 2, 3. So it's basically putting those 2 things together with adding the hydrogens to make sure you have the proper number of bonds on each carbon or oxygen or hydrogen. And then thinking about the skeleton structure to get the backbone first, then it becomes pretty simple. Okay, so let's fire through this table quickly. You should be able to do this, especially if you know the difference between the line formula, the structural formula, which shows all atoms and bonds, and the condensed formula, which takes out the bonds, basically. Okay, so how many carbons are in this first line formula? 1, 2, 3, 4, 5, 6, 7. 7. So 1, 2, 3, 4, 5, 6, 7. And then you can stick the hydrogens on. I'm not going to write them in. I'm just going to draw them as lines. That's another thing that lots of chemists will do, is they'll just put lines and not put hydrogens on the end, because in organic chemistry we make that assumption a lot. And then the condensed formula is a CH3 on the end. 1, 2, 3, 4, 5 CH2s in a row. And then a CH3 at the end. Total of 7. Okay. Now, let's think about this. How many carbons are in this next molecule, number 2? The big question here is that a carbon and is that a carbon? And the answer is NO. The only carbons here are 1, 2, 3. Okay? It's an important distinction that you have to be aware of. So we'll go carbon, carbon, carbon. What's attached to this middle carbon? 2 hydrogens. What's attached to this end carbon here? 2 hydrogens and a chlorine. And what's attached to this end carbon here? 2 hydrogens and a chlorine. Okay? If you draw that as not having the right number of carbons on it, you're going to get it wrong. So you have to remember that if it's a heteroatom at the end, not a carbon. So how would you draw this as a condensed formula? CH2Cl is what we start with. Then we have a CH2 in the middle, and then a CH2Cl at the end. Okay, next guy, number 3. How many carbons do you see? I see 1, 2, 3, 4, 5. This is a 5-carbon compound. It's important that you get that down, get that straight, because if you don't, you're going to get hurt. Don't want you to get hurt. So, carbon, 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 carbon. There's our 5. We're going to stick 3 hydrogens up here at the first carbon. We're going to stick 3 hydrogens here on this CH3 that's sticking down at the bottom. 1, 2, 3 means 1 hydrogen on that carbon. I'll stick it in there. 2 hydrogens on this guy. And then at the end, 2 hydrogens. And then the bromine on the end. Okay, so how do you draw or write the condensed formula? There's a couple ways. After all, this is a CH3 and this is a CH3 that's attached to that carbon. But let's just draw it this way. CH3 to start with, a CH with a CH3 sticking off the bottom, then another CH2, and then a CH2Br at the end. Good. Okay, first time we've seen one with a line structure with one of those. What is that? Well, that's a double bond. All that means is that there's 2 bonds that connect those 2 carbon atoms. So again, let's count our carbon atoms. That's a heteroatom attached to a carbon atom. That's a heteroatom attached to a carbon atom. So this is our first carbon. 2, 3, 4, 5 heteroatoms. So this is another 5-carbon compound. Okay, so carbon, 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 double bond, carbon. That's the way we want to think about this. This first carbon has a chlorine and a chlorine and a single bond. So that's 1, 2, 3, needs another hydrogen. Need 2 hydrogens here. Need 2 hydrogens here. Now, how many hydrogens does this carbon need right here? There's 1, 2, 3. So this only needs 1. This carbon needs 4 bonds. It has 2. One of them is a hydrogen, and the other one is that bromine at the end. Okay, so how do we write this up as a condensed formula? Well, we've got a CHCl2 at the beginning, followed by two CH2s, followed by a CH double bonded to a CH that also has a Br at the end. Practice, practice, practice. Did I mention the practice? Maybe you ought to think about practicing. Lots of examples in the book. Be careful with them. Make sure you check in the back and ask me questions. This is something that's easily done if you practice. And if you don't, you're going to get burned. I don't want you to get burned, so practice. Okay. So I want you to go through the process with trying to figure these out on your own, like hit pause, because if you hit pause and then work it out on your own, then you can compare to see what I have. And if you just wait for me to do it for you, then of course you'll just be sitting there and not being active. You'll be very passive. Look. Never in your life are you going to have, hopefully, knock on wood, a time where you are forced to be at home and not have to go out and do stuff. So we all ought to be writing a novel or learning how to speak French or play the violin or do something spectacular. And of course, one of the things a lot of people are doing is trying to get in shape. So you want six-pack abs, right? Doesn't everybody want six-pack abs? Of course you do. So would this be a way of getting six-pack abs? Subscribing to P98, P90X or Insanity or something like that, and loading it up on your phone and grabbing some Nutella and some Doritos, sitting down on the couch and loading up the video and watching other people work out, watching other people do the exercises, do the crunches. Of course not. You're not going to get a six-pack ab set by watching other people or watching a video. You're going to do it by sweat equity, by going and doing it. Pencil to paper, working hard, figuring out, making the mistakes, getting better and better at it the more times you do it. And that's your job. That is your job, so you got to do that. Okay, so I'm assuming that you've hit pause, you've gone through, you've done all these problems, and now you're going to compare your condensed formulas to mine, which are CH3, 2, CH, CH2, and then C with 3 CH3s at the end. 1, 2, 3. All right. We look at this guy and we have to make sure we have the right number of carbons. 1, 2, 3 in that string with this one here. So that's going to be 1, 2, 3 hydrogens and 1, 2, 3 hydrogens and 1 and then 1, 2. So that helps because we can draw this as CH3 with a CH with a CH3 sticking off the top, and then another CH2 with a Br at the end, and that leaves us with the right number of carbons. 1, 2, 3, 4 with a 5 and a 6. So there has to be total. That group and that group are the same, and that group and that group are the same. And this is a CH, and this is a CH. So you are more than correct to say there are 2 CH3s attached to 1 CH, and then you have another CH with 2 CH3s attached to that. There's lots of different ways to write the condensed formulas, and as long as they're correct, you're not going to get in trouble. They just have to be correct. All right, so what do we got here? 1, 2, 3, 4, 5, 6 carbons. This one has 3 hydrogens on it. 1, 2, 3, so this one has 1. Pardon me, 1, 2, 3, so that has 1. 1, 2, 3, so that has 1. 1, 2, 3, so that has 1. And then 3 hydrogens on that terminal carbon on the very end. So CH3, we want to show these double bonds. So it's a CH double bonded to a CH, CH bonded, double bonded to a CH. That's a single bond, isn't it? That's a single bond right there. And it's a CH single bonded to another CH, which then gets double bonded to another CH. And then there's a CH3 at the end. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. But it tells you that the double bond starts at carbon 2, 1, 2, 3, and carbon 4. 1, 2, double bond starts. 1, 2, double bond starts. Okay. Functional groups. Important to understand functional groups. It's a major topic in organic chemistry because the functional groups are where all the reactions happen. You will learn that the backbone chain, carbon, hydrocarbon backbone chain, is not very reactive, but the functional groups are very reactive. And so identifying the functional group really helps us understand what the chemistry is going to be, what reactions are going to occur, where the reactions are going to occur on a particular molecule. So it's a critical thing, and you have to be training yourself to be really good at thinking about it. And a functional group can be a heteroatom, nitrogen, oxygen, fluorine, phosphorus, any of those halogens. It can be a place where you have a multiple bond or the combination. Okay, so how do we think about it? R is the backbone chain, the hydrocarbon part, because it's not really as important. You want to think of it as sort of the shrubbery before the flower is the functional group. So it's the background. It's the support, and it doesn't really react much. Okay. Okay, so a hydrocarbon, an aromatic hydrocarbon, looks like this. Double bond, double bond, double bond. And it also looks like this. 1, 2, 3, 4, 5. And so because these sort of interchange, you'll see them often drawn like that. And we'll talk more about benzene rings a lot whenever we deal with each of these individual functional groups and how they affect the chemistry of organic molecules. But this is just the basics, the get you started stuff in an effective way. And I guess the best way to do this is alkanes are just basically RH. And that's all that you have. Alkenes, in general, look like this. That's where the double bond is. Alkynes look like this, in which you have that triple bond. And aromaticity shows that you have a ring structure where there's 3 double bonds within. Okay, that's in general how you would identify in a molecule whether you have these. And alkanes aren't really considered to be functional groups because they don't really function that much. They don't really react very much, but we'll continue on. Okay, there's a bunch of other kinds of functional groups as well. Alkyl halides contain a halogen, chlorine, bromine, fluorine, or iodine as part of their reaction. Alkyl means carbon hydrogen. An alcohol group has an OH that's attached. An ether group has an oxygen in between 2 carbon single bonds. A thiol is an awful lot like an alcohol, only instead of a oxygen hydrogen attached, it's a sulfur hydrogen attached. And then amines contain a nitrogen attached to a carbon. And that nitrogen can have just 2 hydrogens, or hydrogen and something else, carbon hydrogen based, or no hydrogens at all on that nitrogen, just attached other carbon hydrogen compounds. We'll watch and look at these as we go. So when we look at an alkyl halide, it's basically RX, with the X being any of the group 7 elements. Fluorine, chlorine, bromine, or iodine. An alcohol has an OH group attached. An ether has 2 single bonds of oxygen to a hydrocarbon chain. Thiol is very similar to an alcohol, but it's an S rather than an O that gets attached to the hydrocarbon part. And the amine, remember, nitrogens want to make 3 bonds and have 1 lone pair. So it's either going to look like that, or it's going to look like that. Those are what amines look like. Okay. Another kind of functional group is called a carbonyl group. The carbonyl is a carbon-oxygen double bond. And these are very prevalent. They're in lots of different compounds, and you have to be ready to see what those are. And again, what we're going to do and what we're doing right now is identifying all the different functional groups and get you to be thinking about looking at a molecule and spying for the functional groups. And then we'll start to look at each functional group and what the reactions are with all of them. But the first thing is to train you to be looking at a molecule and saying, where are the functional groups? Okay, so that's carbonyl. It's attached to 2 other carbon atoms. So you've got C double bond O with 2 lone pairs, and then you've got an R group and an R group. Both of these R's start with carbon. Okay. Now, carboxylic acids are easily confused with alcohols because everybody sees this. But the key is when you're looking at functional groups, you should look at all the groups attached to a carbon that you're looking at, because some of the functional groups have more than one atom attached. Because that's not an alcohol. It's a special thing. It's the carboxylic acid group, the C double bond OH. That's the carboxylic acid, and the whole thing functions all together as a functional group. And an ester, instead of having a hydrogen, it has a R attached. Okay? So you've got a C double bond O, and you have to look past that to see what it is, and then you look at that oxygen and you have to see past that to see what the functional group is. Just takes practice. Amide, or amide, or amide. I've heard it all different ways. An amide contains a nitrogen that is directly related to the carbonyl carbon. So you have the C double bond O, and if a nitrogen is attached directly to it, that makes this an amide functional group. This is not an amine. Why? Because you have to look beyond the nitrogen to say, ooh, it's attached to a carbon. Well, okay, maybe still an amine. Nope, that's a carbon double bond, oxygen. So the whole thing is an amide. Okay. So when I say aldehyde, you have to think about what that is. When I say ketone, you have to think about what that is. You have to keep that in mind all the time. Aldehyde is R, C double bond O, H. That's what the aldehyde is. The ketone is R, C double bond O, R. Carboxylic acid, R, C double bond O, OH. Ester, R, C double bond O, O, R. Then an amide, start with the carboxylic acid group. This time it's got a nitrogen. Okay. So this is one of those deals where you look and you say, okay, what is it? Identify functional group. This is all CH, carbon hydrogen with nothing else, and then it's got an OH attached. So that's going to be an alcohol. This time we have an O in between an R group and an R group. So that's going to be an ether. Single bonds between two R groups attached to an oxygen in the middle. This has just an NH attached to a R group. So this is an amine. C double bond O. Ooh. C double bond O with an OH. The whole thing is a carboxylic acid. Carboxylic acid. C double bond O. That's the first thing to think of. Oh, and an O. So is this an? It could be an acid, a carboxylic acid. Nope, it's got the R group attached. So what do we call that? What do we call that thing? We call that an ester. If we have a C double bond O just with R and R, what's that thing called? That's called a ketone. And then finally, C double bond O with just H. That's aldehyde. And these are your jobs. This is what you have to be able to do. Identify it at any time. So let's see how we did. Alcohol, ether, amine, carboxylic acid. This is not memorization. This is identifying. Ester, ketone, aldehyde. Well done. So now, instead of just having simple molecules, you have to be able to also identify functional groups in great big molecules. So I want you to fight for that. Man, I'm going to insist that you're good at this. This is going to be one of those ones that I always ask you to be able to do. So be ready for it. So battle. Hit pause. Go through. Try them all. There's ecstasy and there's Tamiflu. So go with whichever one you want to go through first. See what you find. Think about how you think about it and see if you identified them all. By the way, we don't use alkane as a functional group here. All right, are you ready? All right, let's take a look. Carbon, carbon, attached single bond to an oxygen. Two places for that. Both of these are ethers. That is an aromatic ring. It's not an alkene with double bond. It's in a ring structure with three double bonds within the ring. That, by definition, makes it something special. It's an aromatic ring. And what do we got here? We got a nitrogen that's bonded straight off carbons, but there's no extra anything on there, so that, or that, doesn't matter, is an amine. Okay, so how about the other side? What do we got here? Okay. This is oxygen, single bond to two different carbons, so that's an ether. Now, do you look at this and say, well, that's an oxygen single bonded to two carbons, so that's another ether? No, it's not, because you have to look beyond the next carbon and recognize that that's a double bonded oxygen, a carbonyl group. So carbon double bond to oxygen, then bonded to an oxygen that has an R group on it, that's an ester. Is this something? As a ring structure, no, that is not aromatic because it only has one double bond. So all we would call this is an alkene group because it's just a double bond. This is NH2 attached to a carbon. So that's an amine group. And then we've got, well, let's see, what do we got here? We've got C double bond O, that's an R, and then we've got an N attached. So all of that together is an amide. Okay, so 1, 2, 3, 4, 5 different functional groups on Tamiflu. 1, 2, 3 different functional groups on MDMA or ecstasy. Your job is to be able to look at these molecules and identify those spots because those are the spots that you're going to find reactions occur. And you're going to have to be able to identify those reactions. Okay. First things first, though. All right, so now we're going to talk a little bit about the properties, the chemical and physical properties of organic versus inorganic compounds. Let's see if these get supplied or whether I have to write them in. Yeah, okay, so organic compounds are mostly carbon and hydrogen, but those heteroatoms, oxygen, sulfur, nitrogen, fluorine, chlorine, bromine, iodine, and also phosphorus. We might even sneak phosphorus over close to nitrogen because they act similar as well because they're in the same group 5A from the periodic table, but that's what organic compounds consist of. Inorganic compounds, also generically known as salts, are metals plus nonmetals. Sodium chloride, potassium nitrate. Sodium chloride, potassium nitrate. That's basically what we're talking about with an inorganic compound. All right, so the atoms that combine to make the compounds are a little bit different. In organic compound, we have electron sharing. Covalent bonding is primarily what we're talking about, whereas in inorganic compounds, it's ionic bonding. So you see ionic bonding going on, you're thinking most likely it's probably inorganic versus organic. Same thing with covalent compound. Okay, there are weak intermolecular forces. You remember IMFs from 111. Weak means they don't want to hold on. The molecules don't want to hold on to each other, which means they easily go up into the gas state or stay in liquid, or can also be solids. Whereas with inorganic compounds, there are stronger intermolecular forces, which means they really want to be solids at room temperature, and it's really hard to melt them, really hard to boil them off compared to organic. What else? Organic compounds are often combustible, flammable. They burn combustion reactions with oxygen gas. This is O2 gas, to form different substances. But we know that we can't burn salt, table salt, so they're in general non-combustible especially compared to organic compounds. What else? Water insoluble in general. Insoluble means does not dissolve. You could even think of it a little bit as oily. So, organic compounds in generally don't dissolve. That's why when you jump into a pool, you don't just dissolve and stay in there because, your skin is mostly organic. As opposed to if you were a salt block, you would dive into water and you would dissolve, and that would be the end of you unless we drained the pool or evaporated all the water, and maybe you'd come back looking the same. That's weird. Okay. Organic compounds, because they have covalent bonding, not ionic, they are not electrolytic. So they don't conduct electricity. They don't form ions in solution for the most part. Whereas we know that ionic compounds often do, because ionic form ionic compounds, and whenever they dissolve, there's lots of ions there to conduct the electricity, and therefore we consider them to be electrolytes. Okay. So moving in the opposite direction, if a compound has a high melting point, would you consider it to be organic or inorganic? High melting point means hard to dissolve. High melting point has to do with high or strong IMFs, and therefore inorganic. This isn't about memorizing. This is about understanding that high melting points mean high intermolecular forces. Not soluble in water. This has to do with covalent bonding, right? Versus ionic. Because ionic are the ones that dissolve in water. So because it's covalent, we're going to consider that to be organic. See, this is, again, this isn't memorizing. This is about understanding what's going on. Oh, so this is carbon and hydrogen mostly. Of course, that's organic. This is a metal plus a nonmetal. So of course that's ionic. Burns easily in air. Combustible, right? Very flammable. You don't sprinkle salt on your fries but then stand back because it bursts into flames. No, doesn't happen. Not even if you sprinkled it on a flame would it burst into flames. And so ionic compounds don't act that way, but covalent organic compounds do. And covalent bonds. All right, so let's see if we're right. I think we're right. I feel confident about this one. Inorganic, organic, organic, inorganic, organic, organic. Okay, good, excellent. So I'm sort of losing my mind here. We're getting towards the end of the PowerPoint presentation, set one. And so let's see if there's anything left for us to look at. Polarity properties. Yeah, we got dealing with polarity, that's for sure. Okay, so this is polarity both. Well, let's deal first with the whole idea of the bonds, okay? We talked about this a little bit already. This has to do with changes or differences in electronegativity. So identical or similar electronegativity compounds, or I'm sorry, elements that bond to each other makes it nonpolar. Because the EN differences are very, very small between carbon and hydrogen and carbon, all of these are nonpolar bonds in organic compounds. Let's say organic chains. Okay, now a covalent bond can become polar when you have different electronegativity, and we're talking about heteroatoms, right? NO, the halogens, phosphorus is in there as well. That's when we start to run into polar bonds, where there's a partial positive and a partial negative, and all the heteroatoms are partially negative compared to the carbon. Good. So that's for polar bonds. Polar bonds are different than polar compounds. We have to think about not just bonds, but also the molecules as a whole. And this is also, this is sort of like magnets with a plus and a minus, with a north and a south. And it also has to do with tug of war. You'll see what I mean in a second. We have to have polar bonds in order to have a polar molecule. But just because a molecule has polar bonds does not make it a polar molecule. You'll see what I mean shortly. If it's just a hydrocarbon, we have nonpolar bonds, so it's a nonpolar molecule. No polar bonds, no polar molecule. When that happens, the IMFs are weak, very weak. And that's why they like to be gases or liquids, because it's easy to get them to escape from each other and jump into the gas phase. When we have a bond that is polar, we often can make a positive end of a molecule and a negative end of a molecule. So that's where it looks like a magnet, sort of a north-south. And whenever there's a side of a molecule that's negative and a side of a molecule that's positive, that's when we have a polar molecule, because you have dipole-dipole interactions. The IMFs are stronger. And if you have hydrogen bonding, that's even stronger. That's the strongest one yet. It's the strongest intermolecular force there is. So, even though these two compounds are relatively close in size, one of them is a gas and the other one is a liquid. And I think you can tell that this one would be the gas and that this one would be the liquid. Okay. So continuing on with molecular polarity. If the individual polar bonds in a compound cancel out, then the molecule is nonpolar. So yes, do you have polar bonds here? Sure. Partial positive, partial negative, partial positive, partial negative, but the pool is exactly the same. If we are playing tug of war and this is the flag, the flag doesn't move towards the left or towards the right. It stays exactly the same. If nobody wins the tug of war, therefore non-polar molecule. However, there's nothing more negative than an electron lone pair. And remember, this isn't flat, this isn't linear, this is tetrahedral, so the shape is bent. Which means it's partial negative up here and partial positive down here. The tug of war goes this way. It's way more negative on one side of the molecule compared to the other side. And so therefore this is polar, or it has a dipole. So it's a polar molecule. Okay. So you have to look at the Lewis dot structure to determine the shape to then decide whether or not the poles cancel out, to see whether or not the molecule itself is polar or nonpolar. And that becomes really important for things like whether or not it dissolves in water and the kind of reactions it might undergo. Okay, so whenever we're talking about solubility for organic molecules, like dissolves like, just remember that. Like dissolves like. What do we mean by that? Most organic like with like. Okay, so if it's nonpolar, it's going to dissolve in nonpolar solvents. But if it's polar, it's not going to dissolve in a nonpolar solvent, and vice versa. Hydrocarbons and other nonpolar are insoluble in water, which is very polar, right? Because think about it. For places, tetrahedral geometry. So you've got oxygen with a lone pair and a lone pair and a hydrogen and a hydrogen. So that's bent. So it's partial negative, partial positive, bent shape. So water is a polar solvent. It's important to think about that. Polar organic compounds. So if you have an organic compound that happens to be polar, it's water soluble, but only if they're small and only if there's a nitrogen or oxygen that can do intermolecular force hydrogen bonding. So most organic will dissolve in organic solvents. The question is whether or not they will also dissolve in water or not. And the answer is, it depends. Like, for instance, ethyl alcohol is an organic compound. Does it dissolve in water? Sure. Beer doesn't look like Italian dressing, right? It's not oil and water. It's dissolved. But ethanol is a very small organic compound. But oil is a very large organic compound, and it won't dissolve in water. See, your real life experience is obvious to you if you just know how to think about it. And the polarity of an organic compound decreases as the number of carbon atoms increases. So bigger organic equals less polar or more nonpolar. It's the best way to think of it. Okay. So we look at something like hexane and we decide, is it soluble or not? What is it soluble in? So let's first decide in water. Well, there's no oxygen or nitrogen present. It's pretty small, but there's no oxygen or nitrogen present at all. So it's organic, so it's soluble, but there's no, it's completely nonpolar, so therefore it's water insoluble. That's the way you want to think about that one. What about ethanol? It's got an oxygen, it's small, and it can form hydrogen bonds in two different spots, right? So it's definitely going to be able to be soluble in water because it's small and it's got oxygen, so it can form hydrogen bonding. But it's also going to be organic soluble because it's an organic compound. Cholesterol, a very large molecule. Yep, it's got oxygen. And it's even got OH. But because it's so huge, so much of this is non-polar with this tiny little bit of polarity here at the end. It's definitely going to be organic soluble, but it's not going to be water soluble because it's just too big. Okay, good. So if we're going to look at an organic compound and we're going to try to predict the water solubility of each, I mean, it's organic. So organic solubility of organic compounds. Yes, it's always. Organic compounds will always be soluble in organic solvents, period. We just have to decide on whether or not they're going to be water soluble. So we look at octane and we say, I don't know, that's 8 carbons. That's pretty big. And it's definitely non-polar, right? Because there's no O or N. So we're going to say that this is insoluble in water. Acetone, small. O is present. I'm going to say yes, water soluble. I mean, it's a polar compound. Oxygen is present. Okay, but look at that. It's huge. And nonpolar in that huge part because it's nothing but carbons to hydrogens in the sort of the chain. Sort of looks like this. This is all the nonpolar part, so it's not going to want to be. So no, this is going to be organic soluble, but water insoluble. Will not dissolve in water. Okay. Yep, insoluble in water, soluble in water, insoluble in water. Very good.